Okay, so I'm very happy to be here to talk about my recent work on GMRES in collaboration with Daniel Shields, who's professor at Temple University in Philadelphia. When I started working on GMRES earlier this year, I gave a talk in the Rencontre INRIA et GLL, and I think we've made quite a lot of progress since then. So this is what I'm going to show you today. Okay, so here's the problem I'm addressing. I'm addressing solving linear systems. My matrix is called A. It is an order n matrix in the field of either real or complex numbers. I'm going to make the assumption throughout the talk that A is non-singular, so the linear system has a solution. And there are going to be a few other assumptions that I'm going to make along the way. I try to make as few assumptions as possible, but I end up making more and more assumptions as the talk goes on. So I'm considering cases of A that's non-Hermitian, so that's going to follow all the way through. I start off with any non-Hermitian A, but then later on we look at positive definite A. I usually have in mind that the order of A is very high. So we're going to have to use parallel computing at some point. Okay, there's not an option to just use a direct solver. A is usually sparse, so of course we're at free fem days. So the typical application is a matrix that comes from the finite element discretization of a PDE using free fem. And in the numerical section, I make more assumptions because I'm using domain decomposition, but I can talk about that when I get to it. So the two fundamental questions that I'm addressing with my work and that I'm going to address today is how fast does GMRES converge? How can we predict how fast GMRES is going to converge? And how can we accelerate convergence of GMRES? So I'm not assuming that anybody is hearing about GMRES for the first time, but I still want to introduce GMRES completely. So GMRES stands for Generalized Minimal Residual Method. It was introduced by Stad and Schulz in 1986. GMRES is an iterative solver, so you feed it an initial guess, x0, and then at each iteration, it computes, actually indirectly computes, an approximate solution xi, which minimizes the residual over the space, which is x0, initial guess, plus the Krylov subspace. And the Krylov subspace is here. It grows at every iteration by adding one vector to the base. So that's GMRES for you. And so my long-term objective, which I partly achieved today, is to provide a way to choose accelerators for GMRES, specifically a preconditioner, a weighted norm, and a deflation operator, which ensure that GMRES is going to converge fast for the problem that's considered with respect to a convergence bound, which must be proved or chosen. Okay, for GMRES, there's no one convergence bound which everybody agrees on. This is the best convergence bound. It's very general and it's easy to use. So this is still also a work in progress, finding the right balance. So here's the outline. I'm going to first present preconditioning and weighting. So preconditioning is by H, weighting is by W. It will be at the top of every slide in case you forget the notation along the way. Then we see how GMRES converges by considering it as in an equivalent form, which is GCR, the generalized conjugate residual algorithm. Then I will look more specifically at the case where A is positive definite, show you numerical results, and in the last part, I'll introduce spectral deflation and show you more numerical results. So I told you I'm going to accelerate GMRES with preconditioning and weighting. So first of all, preconditioning is by H, a matrix which is non-singular, and instead of solving AX star equals B, I solve HAX star equals HB, or AHX star equal B. So this is left and right preconditioning. Okay, this should be U star. So I'm sure you've all seen this before. And then the weight matrix is something that maybe you haven't all seen, but it's really simple. In GMRES, I told you at every iteration, the solution minimizes the residual. So I didn't specify, but it minimizes the residual in the Euclidean norm. However, you can very easily change the norm which you minimize in GMRES. So just every time there's an inner product in GMRES, you replace it by a different inner product. So my inner product is induced by a matrix W, which is HPD, okay, W for weights. And what happens when you use a preconditioner and a weight matrix is that the way that the iterates are characterized changes slightly. So this is the case for left preconditioning. The preconditioner gets put into the Krylov subspace here. And for left preconditioning, it also gets put into the residual that is minimized. So you minimize the preconditioned residual, and the weight appears here in the definition of the norm that you're minimizing. Okay, so preconditioning and weighting actually don't do the same thing. And then right preconditioning is the same, except that you minimize the norm of the original residual here. So that's H and W, and in order to choose them, we're going to prove a convergence band for GMRES, which makes the role of H and W appearance. So to do this, I consider GMRES in its GCR form, which is on the slides here. I'll talk about it a tiny bit after. And if machine precision is infinite, then GCR and GMRES produce exactly the same iterates. So by this, I mean that GCR also satisfies this formula here. At every iteration, the residual is minimized over x0 plus the Krylov substance. Okay, so to introduce the algorithm, I'm going to very quickly prove this result. In the algorithm, so here I go into the iteration, and then in the iteration, there are two steps. So the second step is here, and what it does is that it adds one vector to the basis, the basis for the Krylov subspace. Okay, so my claim is that Q0 to Qi minus 1 is a W orthonormal basis for A times the Krylov subspace. And this is because here we're just doing a Gram-Schmidt procedure. And then the second thing that happens in the iteration is up here, where we update the approximate solution and update the residual in a way that ensures that this formula holds. Okay, so precisely, if I want to prove star, okay, so star is equivalent to this minimization property, which is equivalent to the fact that R0 minus Ri is the W orthogonal projection of the initial residual onto A times the Krylov subspace. And then this is just the formula for the orthogonal projection. And I have an orthonormal basis. And here, this is a coefficient alpha j, which is here. Okay, there's a little step to show that the alphas are equal, but there's not much to it there. And now that I have this form of the algorithm, I can very easily look at what happens between iteration I plus 1 and iteration I. So I take the update formula, which was Ri plus 1 equal Ri minus alpha I Qi. I flip it. I recall that I have this orthogonality property, and then I apply Pythagoras in the W norm. Okay, so here I'm just replacing the quantities, and so I get a first bound here. And this bound I don't really like because I don't really know what to do with the inner product between Qi and Ri. Okay, I want things that look like spectral equivalences between matrices. Okay, no problem. I apply in one of the a formula from another part of the algorithm. I'm not going to go into the details, and then I can replace the numerator by AHRI. Okay, so what I want to insist on is that up to now, here I still have an equal sign. Okay, this is the exact formula for the decrease in residual between iteration I plus 1 and iteration I. And now I'm going to make an approximation. So now what I want to do is I want to get rid of this Qi, get something that depends on Ri instead. And then I can do in for soup over all the Ri's in k to the n, and I get a convergence band. And to do this, I use the formula by which I calculate Qi. So Qi is the new vector in the Krylov subspace, which is AH times the previous residual, orthogonalized. This is just what comes from the Gram-Schmidt formula. Okay, so the vectors are pairwise orthogonal. So again, I can do Pythagoras and I get this here. Okay, and then I just strike out this term here, the sum of the QJs. And this is where I stop having inequality and I get an inequality. And my convergence bound is this bound. So what I've done here is that I have neglected completely the good that comes from the orthogonalization. What this also means is that the bounds that I'm proving and the Elman bound and the bounds that I'm going to use throughout my talk are also true for all restarted versions of GMRES, all truncated versions of GMRES, and even minimal residual where you don't orthogonalize at all. Right, so this bound, I just copy it here again, and then if I group the terms in a certain way, I have reproved the Elman bounds from this from 1983, and it's just a way of grouping the terms in this bound. Okay, so this is quite well known. This is the field of values, but I don't especially need it, so I'm not going to insist too much on that definition for people who don't know it yet. Okay, so I said I want to make as few assumptions as possible, but to move on, I actually had to make more assumptions. And the first assumption that I'm going to make is that I'm going to use a Hermitian preconditioning. Okay, but before I do that, I need to introduce a notation for the Hermitian parts of the matrix A and the skew Hermitian parts of the matrix A. So I'm going to write this on the board, even if not everybody can see it, because I use this all the time. N of A. This one is Hermitian. And this one is skew Hermitian. And the reason this pops out is that every time I evaluate the inner product between AX and X, I can make apparent the Hermitian part, the skew Hermitian part. And then when I take the modulus here, it's larger than the evaluation of Hermitian parts of AX in a product with X. Okay, so that's why this is going to pop out of our estimates. So here's the proof of my bounds. It's very simple. So this is the term that I had earlier, except now I want to have a bound. So I just take the inf over all the possible realizations. Okay, before y was Ri. Then I use my assumption, which is that my preconditioner is Hermitian positive definite. And I make one more assumption, which is that as a weight matrix, I use the preconditioner. So now I'm going to minimize the residuals in the preconditioner norm. Okay, I do that. I inject it into the bounds. Then I do a small change of variables. Then the inf of the product is larger than the product of the infs. I do another change of variables here. Then I do my trick where I replace the matrix by its Hermitian parts. Okay, remember the trick that I showed you on the slide before. And then I multiply by this term here. Okay, at the top, at the numerator here and at the denominator here. So I have three terms. In order to make these terms more precise, in order to use this bound, I make one last assumption, which is that the matrix A is positive definite. So the matrix A being positive definite means that M of A is Hermitian positive definite. And then great things happen. So here's the bound again. Here, this one here is a Riley quotient for lambda min, smallest eigenvalue of the preconditioned symmetric parts. This term here is a Riley quotient, which is bounded by lambda max of the preconditioned Hermitian parts. And this last term here can be bounded using a bound that comes from the work of Johnson by 1 plus the spectral radius of Hermitian parts of A inverse N of A. Okay, the spectral radius is the norm of the eigenvalue of maximal norm. And now I have a bound for GMRES that depends on how well my Hermitian preconditions the symmetric parts and how non-Hermitian my problem is. Okay, this spectral radius of M inverse N measures whether the problem is very non-Hermitian or only mildly non-Hermitian. So here's the bound again, and here's another conclusion that I can draw from it. If I have a good preconditioner for the Hermitian parts, then a lot of the properties can carry over to the non-symmetric, the full problem too. For example, if I have a preconditioner for the Hermitian parts, which provides a scalable algorithm for M of A, then I can apply the same preconditioner to the full problem, to the non-symmetric problem, and my convergence bound is still a scalability result. Okay, if this term here does not depend on the number of processors, then this term here doesn't either, because there's no notion of parallel computing in this term here. Okay, so one example is if I'm solving a PDE for which I can use domain decomposition with the Genio core space, then I get a nice bound that depends on the multiplicity of the mesh elements in the partition into subdomains and the threshold that we set. And so this doesn't depend on the number of subdomains. Okay, so my claim is that if it scales for the symmetric parts, it scales. So let's test this theory on the most simple problem that I know that fits my assumptions, which is the advection diffusion reaction problem. So here's the PDE. This is the variational formulation. The symmetric part is here. The skew symmetric part is here. My convection field is a rotating convection field. And here I solved the problem with free fem, of course. And before I show you the numerical results, there's one more thing that happens for this particular problem of convection diffusion, which is that convergence does not depend on little h either. Or rather, the convergence bounds does not depend on little h either. If I'm using Genio. So if I'm using Genio, condition number of preconditioned permission part doesn't depend on the discretization step. And this spectral radius of M inverse N does not depend either on little h. Okay, so this result I found in the paper that's cited here. So let's check that when I solve the problem, I get convergence that doesn't depend on the number of subdomains, doesn't depend on the discretization step. I'm using FFDDM, thanks to Pierre-Henri Tournier, who helped me to set it up. These are the parameters for the Genio, for the setup of the preconditioner. And these are the iteration counts. Okay, doesn't depend on number of subdomains, doesn't depend on little h. Now, of course, it does depend on something, which is how non-symmetric the problem is, or how non-Hermitian the problem is. Okay, so this row of m-1n doesn't depend on little h in this case, doesn't depend on the number of subdomains, but of course it depends on the strength of the non-symmetry. Okay, so here iteration counts grow when the problem becomes more non-symmetric. Okay, I could make it blow up completely. I didn't hear, but I'm of course not claiming that I have solved that problem. The way that we are trying to improve the fact that we miss out completely on the non-symmetric part of A is by deflation. So this is very recent work that I've done with Daniel Schiele on spectral deflation. So if you recall the bound before, our problem is with the term spectral radius of m-1n. So really what we want to do is to make this spectral radius small. So if you're used to deflation and spectral coarse spaces, you want to deflate the eigenvectors that correspond to large eigenvalues of m-1n. And you hope that that will improve convergence. Well, the idea that I said in a few words works. So here is the deflation operator. So where it's hidden, it says deflation. And deflation is also called projection preconditioning. And you define the deflation operator by choosing two matrices, Y and Z, which are long, tall, and skinny matrices, which have m vectors in them that span the deflation space. Okay, and you want m to be far less than the size of your original problem. Then you introduce these two projection operators, and solving AX equals B is equivalent to solving the problem projected by PD and the problem projected by I minus PD. And then this notation conveniently allows us to pass the projection to the right of the operator. And in the end, we have two problems. One of them is for a matrix of small rank, if the number of vectors in your deflation spaces is small. So you solve that one by a direct solve, you pre-solve it, and then you're left to solve the remainder with your Krylov subspace. Okay, so that's a very quick introduction to deflation. Now, in non-mathematical words, what we try to do with deflation is we try to identify the parts of the problem that is hard to solve, and we project that part of the problem out of the original problem and solve that one with a direct solver. So here I did my convergence proof again, this time with the projected operator, and I get the same bounds as before. Okay, 1 minus, here is the condition number of the preconditioned Hermitian parts. This is the same term as before, except that now I don't minimize over all the y's in Kn, I minimize over the kernel of something related to my deflation space. So the vectors that have not been deflated. I'm nearly finished. So a minus 1 can be written in this way. Okay, and then the MA minus 1s basically cancel out, and we end up with a spectrum, something that depends on the spectrum of M minus 1 N. So then I solve this eigenvalue problem, which is a very special generalized eigenvalue problem, because on the left, I have a skew Hermitian matrix, and on the right, I have a Hermitian positive definite matrix. So this has nice properties. First of all, I can build a basis of vectors that are orthonormal in the Hermitian parts of A, and the eigenvalues are either 0 or they're purely imaginary in complex conjugate pairs. Okay, so here's the theorem. If I deflate all the vectors that I don't like, so all the vectors which correspond to an eigenvalue larger than tau, of course I called it tau again, for this eigenvalue problem, then the convergence bound for GMRES is as follows. Okay, so we have the condition number of the preconditioned Hermitian parts and this threshold, which is, so the tau is the first eigenvalue that you don't deflate. Right, does it work? Ha. So I solved the same problem as before. It's the same equation. I just put a parameter here, eta, so that I can make the problem more or less non-symmetric. And I solved the eigenvalue problem. I plotted the eigenvalues here. And anybody who's used to GNO or spectral core spaces at this point goes, oh, because we really wanted there to be a gap in the spectrum, right? We'd love for there to be a few large eigenvalues, and when we deflate them, oh wow, the bound becomes great. Well, that hasn't happened here. All the eigenvalues are sorts of in the same parts of the domain. Okay, but we can still apply it. So this is a problem that is not very non-symmetric. I'm deflating more and more eigenvectors, and convergence improves. Okay, I'll grant you that deflating 1,000 vectors to save 10 iterations is a slight overkill. But this problem was, I mean, we were happy with just the Hermitian preconditioner. This problem is more non-symmetric, and here we start to see that maybe deflation is a good idea. Okay, so with no deflation, 350 iterations, and I deflate 100 vectors, and I get 275 iterations. So something is going as planned. Okay, I'll have to skip this because I've gone over time already. So the takeaway is that weighting, preconditioning, and deflation can work together to give a fast method. But in order to apply this strategy, you need a convergence bound that allows you to do this. So I used the field of value bound, okay, a generalization of it. This bound has some restrictions. One of the most important is that it misses completely the superlinear convergence behavior because it ignores completely the orthogonalization, but it's still open. What are the other options? And they also introduce an algorithm that scales if it scales for the symmetric parts. And the last results that I showed you, shame on me, were computed with Octave because I didn't manage to do the global deflation with FreePen.
Because it's complex.
Even in the real case. Yeah. Okay, thanks for your attention.
Pierre-Henri, you have to work.
Yes, Pierre-Henri already helped me to compute the vectors, and now we have to deflate them.
Okay, so time for one short question.
Seulement s'il n'y en a pas d'autres. Allez, vas-y.
Is this related to the ether? The parameter
Yes.
Is there an optimal optimality for just to keep the convergence?
I don't know yet. It's a very good question. I don't know. I haven't played with it enough yet.
Talk about that.
Okay.
Okay.